Hi folks, welcome to Unit 5, Lesson 7. So what we're going to do today is go through a few different examples using the different forms of the equation of a quadratic function that we've studied. So what we're going to do is we'll stop the video every once in a while, give you some time to have a look at the problem, and then we'll take it up together. Okay, so I'm going to ask you to take a look at number 1, where the information is given on a table of values. So the information is given numerically, and I'm going to ask you to eventually come up with an equation, so an analytical model for this function. Okay, so please stop the video now and take some time to work on this problem. Okay, we're back. So let's take a look here. The first question says, confirm that the function is quadratic. So the way to do that when the function is given a table of values is to see whether the second differences are constant. Now, of course, in order for that to work, we need the x values to be going up by the same amounts, and we see that they are. They're always going up by 0.5. So we're going to start by finding the first differences of these y values. Okay. So remember, always the second minus the first. So 3 minus 7.5 is negative 4.5. And then here 0 minus 3 is negative 3. And then negative 1.5 minus 0 is negative 1.5. Negative 1.5 minus negative 1.5, well, that's 0. Whether you add or subtract doesn't matter. And now here we see that things are starting to go up. Okay, so here we're going up by 1.5, and then we're going up by 3. All right, so those are the first differences. They're not constant, so this is definitely not a linear function, which I don't think we were expecting it to be. All right, and now we'll do negative 3 minus negative 4.5. So that's going to be plus 1.5. Okay, negative 1.5 minus negative 3 is like plus 3. So again, plus 1.5, and we see this is looking pretty good. So this is 1.5. So plus 1.5, again plus 1.5, and plus 1.5. Okay, so we have, okay, since the second differences are constant. All right. So now we know that when we're looking for the equation or an equation for this function, we're looking for a quadratic equation. All right, always good to check before you go ahead and start. So the question is what type of information is given? I look here and I notice that I do have the y-intercept, which is 7.5. So if I wanted to use standard form, I would know the c value, but there's no real way to determine the a and b values in that function. Okay. So I might look for the vertex, but I see there doesn't really seem to be one highest or lowest point where the points to left and right are repeating each other. There is some repetition, but there is no highest or lowest point on this table of values. So it doesn't look like vertex form is going to work, but I do notice here 2 points where the y value is 0. And of course, remember that points where the y value is 0 is just the where we find the x-intercepts. So what we have here is we have x-intercepts of 1 and 2.5. So I'm going to work with factored form. So factored form is just y equals that a value that shows up in all three forms times x minus one of my intercepts, which is 1, times x minus the other intercept, which is going to be 2.5. All right, and as we have when we're working with vertex form, the only thing that's left to do is to find the a value. All right, so I'm going to pick nice points here. Anything other than the x-intercepts, because I've already used those, and I think I'm going to go for 3, 3, just because it's the only one that doesn't involve any decimals. So y is equal to 3 when x is equal to 3. So y equals 3, a, then here we have 3 minus 1, and then 3 minus 2.5. All right. So let's do this here. We have 3 is equal to, so 3 minus 1 is 2. And then 3 minus 2.5, well, it's just 0.5. So 2 times 0.5 is just 1. So there we go. We actually have that a is equal to 3. All right. So we can now write our model. Y is equal to 3 times x minus 1 times x minus 2.5. All right, and so now they're asking us to determine the vertex, axis of symmetry, and maximum or minimum value. Now, these are things that we normally would get from the vertex form, but we can get these also from factored form with a little bit of work. So here, this is a parabola going upwards, okay, and because we know these 2 points, level points at the x-axis, we know that the axis of symmetry, and hence the vertex, is going to be located right in between. So our h value for the vertex, which is also what's going to give us our axis of symmetry, is just given by the average of our two x-intercepts. So 1 plus 2.5 divided by 2. So this is 3.5 divided by 2, which is going to be 1.75. All right. So now if I want to find, so this is going to give us our axis of symmetry, which we'll write out later. But if I want the maximum and minimum value, I need the k value, the y value of the vertex. So now that we have the x value, we can just stick it into the equation and determine that y value. So our y value, in this case, specifically the k, which is the y value of the vertex, is just going to be given by 3 times 1.75 minus 1, and then 1.75, minus 2.5. And now we can solve for this y value here. So 3 times, so this is going to be 0.75, and this is going to be, well, actually, that's just going to be negative 0.75. All right. And this here, I don't think I'm going to do this one in my head. So let's get our trusty calculator. And we have 3 times 0.75 times negative 0.75. And so we have negative 1.6875. Okay, so now let's answer the questions that they're asking us. So determine the vertex. Well, the vertex is just going to be 1.75. Whoops. Forget that there. And negative 1.6875. Okay. What's our axis of symmetry? Now remember, the axis of symmetry is a line. It's a vertical line. So the axis of symmetry is going to be x equals 1.75. Okay, not just 1.75. 1.75 is a number. X equals 1.75 is a vertical line. And lastly, the maximum or minimum value. Well, in this case here, because the a value is positive, it opens upwards, so we have a minimum value. So our minimum value is just the y value of the vertex, which is negative 1.6875. All right. So just to recap, we can determine whether something's quadratic from a table of values by checking the second differences. Once we know it's quadratic, we look for what information leads us to one of our forms for the equation line. In this case here was factored form. And then once we have factored form, we can actually find some stuff with regards to axis of symmetry, max, min, and vertex. Okay, so the next thing you're going to do is work with this question here, and this is, a real life scenario. So what I strongly recommend you do, as I say with an exclamation point there, is to draw a diagram. But of course, if you want to then use all your tools of algebra and functions, you're going to want to place on this diagram a Cartesian plane so that you can then determine an equation. All right, so take 7, maybe 6, 7, 8 minutes to work on this one, and stop the video, and we'll be back. Okay, so we're back to number 2. So let's see what it says. It says a hockey goalie lifts the puck from the ice, sending it clear across the rink. So a couple of things that are going on. So the goalie actually starts the process on the ice, okay, and lifts it, so that means it's going to be going up and then eventually down. Okay, so it's intercepted at the opposite goaltender, 2.8 seconds at a height of 1 meter off the ice. Okay, but they give us some information. They said, well, had she not done so, the puck would have hit the ice 0.2 seconds later, landing in the goal. All right, so let's see if we can draw a diagram here. So I think it's pretty clear that our x-axis is going to be the ice. Okay. The question is where to put my y-axis? Well, I might as well put my y-axis at the time at which this whole process starts. So often when we're working with time, so height versus time, we sort of start things whenever the whole process started. So it starts when the goalie hits the puck. So it starts off at the ground, okay? And there we notice, hey, or on the ice, hey, that's one of our X-intercepts. And then it goes up, gets lifted, goes up, and then eventually comes back down. But a meter above the ground, it gets stopped. Okay, and where does this happen? Well, it happens at a time value of 2.8, and at a height of 1 meter. So 1 and 2.8. So this point here is going to be 2.81, likely useful for us. And then they give us more information. They say, well, had the goalie not stopped the puck, it would have gone down and it would have touched the ice 0.2 seconds later. Well, isn't that nice? It already went 2.8 seconds of time that elapsed. Another 0.2 seconds would mean that it would hit the ice at exactly 3 seconds. Okay? And so now hopefully you saw that what we have in terms of this parabola are the two X-intercepts, okay, and some other piece of information, okay, except we're not looking for any of this stuff. We're looking for the maximum height, okay, but this hopefully makes you think of what we did in the previous question, that if we can get an equation in factored form, that could lead us to information involving the vertex. Okay, so let's look at how we can solve this problem here. So again, I'm going to start with factored form. So a times, so what are my two X-intercepts? Well, 0, so x minus 0, which is just going to become x. And then even though the puck gets stopped, remember, all we're doing is refining the equation for this parabola. Okay, so this parabola would have another X-intercept at 3, and then we'll use whatever part of the parabola is useful for us, which in this case here will be that maximum point. Okay, so x minus 3 will be the other part. Okay, so now in order to find a, I can now input the point that I know. So y is equal to 1, x is equal to 2.8. I guess I didn't really need to write that, minus 0. Okay, so what do we have here? We have, this is just going to be 2.8, and this is going to be 2.8 minus 3 is negative 0.2. I'll write it out. So 2.8, and this is going to be negative 0.2. Now, this isn't going to be a particularly nice number, and I'm going to have to divide it to 1. But since this is an application type problem, so something that's got a physical context, it makes sense to be approximating. So let's find a here. I'm going to divide that to the other side. Okay. So what do we have? We have 1 divided by, and make sure you open up a bracket because you're performing an operation in the denominator, 2.8 times negative 0.2. And that's negative 1.78, I guess 6. Okay. So now we've got our model, y equals negative 1.786, x times x minus 3. All right, but what we're looking for is the maximum height. So we know it's going to be a maximum because of the a value being negative. So let's start by finding the h value of the vertex, which is just the average of the two X-intercepts. So 0 plus 3 divided by 2. So that's just going to be 1.5. And now to find our maximum value, that's just our k value, okay, which is just the y value of the vertex. All right, so we're going to stick this into the equation. So we have negative 1.786 times 1.5 times 1.5 minus 3, which is just going to be negative 1.5. So let's put this on the equation, and luckily I kept that number. It's already there. So times 1.5 times negative 1.5, and it looks like we've got just about 4 meters. Okay, so since everything was given, yeah, there we go. I was looking for where we had meters, and it gives us a height of 1 meter. So all of this is in meters. Okay, so this was similar to the previous one that we just did, except, you know, we had a context, we drew our picture, we laid on the picture a Cartesian plane, and then from there we were able to use our knowledge of functions to come up with a way to solve it. All right, so let's take a look at the next one. Okay, so in this one here, they're asking you to determine an equation given the graph. So now we're going from a graphical model, again, to an analytical model. So take some time, maybe 5 minutes to work on this one here, and we'll take it up. So please stop the video, and we'll be back in a bit. Okay, we're back. So let's take a look at number 3. And I noticed something a little different from the ones we just solved because it's not very clear what the x-intercepts are. Okay, they're certainly not going through one of the corners of our boxes here, but I do notice that the vertex is pretty clear. Seems pretty certain that the vertex is at 3, 5, or if it's not at 3, 5, it's very close. And again, anytime we're working with a graph, we sometimes have to approximate, but that's pretty good. So I think I'm going to work with vertex form. But of course, we need some other information. So I look here, maybe a little tough to see, and I'm not seeing any points that really fall. This one's close to being at 1, 2, but I think what a nice point is this y-intercept. The y-intercept seems to be at 0, -1. So I think that's what I'm going to use as my second point. So let's start off. This time, instead of using factored form, we're using vertex form. So a times x minus the x value of the vertex is 3, okay, squared plus k, which is the y value of the vertex, so 5. And now I'm just going to input this point into the equation to solve for a. So here y is equal to -1, x is equal to 0. Okay, so here we've got -3 squared is 9, so 9a, and bring the -5 to the other side, so it's going to be -6. So a is equal to -6 over 9, or a is equal to -2/3. All right, and there we have it. There's our equation. Y equals -2/3, x minus 3 squared plus 5. Okay, so just to recap here, going from a graphical to an analytical model, but the important thing here is to work with as nice a set of values as you can. In this case here, it wasn't the x-intercepts, it was the vertex. So that's why I worked with vertex form. All right. So let's just take a quick look at number 4 before you take some time to work on it. So it says the point 39 on the function y equals x squared is transformed to this point here on another parabola. Okay. Give 2 different sets of transformations that could accomplish this. Okay, so there seem to be indicating that there could be more than one way to transform y equals x squared so that it turns 39 into the point 817. Okay, so I want you to try to do this, and I'd like you to actually write out the equation for the transform parabola that accomplishes this. Okay, so take maybe 5 minutes or so to work on this, and then we'll be back in a little bit to take it up. Okay, please shut the video. Okay, we're back. So let's take a look here, and we need to start with the point 39, and we need to get to 817. So I would say for our first example, let's take the most direct route. And the most direct route would be to only do additions and subtractions. Okay, so what I can do here is if I add 5 to the 3, I'm obviously going to get x equals 8. And then here I'd have to add 8 to the 9 to give us 17. Okay, and that gives us the point we want. So the question is, what transformations are these? Well, we're moving 5 to the right horizontally, and then we're moving 8 up vertically. All right. But if I want to write the equation, this is where I have to be careful, because remember that anything that's horizontal will always have the opposite effect to what we see in the equation. So if we're going 5 to the right, we're actually going to see x minus 5 in the equation. And then if we're going 8 up, anything vertical follows the same operation. So in this case, plus 8. Okay, so this is one that'll work. and then second one here. So again, since we don't deal with multiplicative transformations for x, I'm still going to be adding 5 to 3 to get to 8, because I don't want to deal with having to multiply the x by some value, and we showed that it was unnecessary in a previous lesson. So now we have to find another way to get 9 to 17. Well, I see a pretty easy one, because if I multiply 9 by 2, 2 times 9 is 18, and then I'll just have to subtract 1 to get to 17. So this series of operations will get me to the same place. All right. Now, this is not going to be the same parabola. It's just this point happens to be transformed exactly to 817. So what would this look like? So again, we'd have x minus 5 squared. Okay. But we're multiplying the y values by 2. So that's going to give us an a value of 2 in front. And then we're subtracting 1 from the y values. And that's going to give us our k value of minus 1. Okay, so there we have it. And if you wanted to graph both of these on Desmos, you would see that they would both have the point 817. All right, so let's take a look at this last one. This will be a last one for today. And this is actually going to give us a bit of an idea of what we're going to be doing over the next couple of units after this one. So it says for each quadratic function, which they're both given in vertex form, as you see, they want us to determine the x-intercepts. Okay, so we saw previously that if you had factored form, which gives you the x-intercepts, you could determine the vertex. Can you go backwards? Okay, and the answer is, well, yes, you can. Okay, when you're in this form here, and the hint I give you is to use good old-fashioned algebra. So I want you to think this is actually something that you could have accomplished back in grade 9. Nothing fancy here. Just make sure you're following your rules of arithmetic and algebra correctly. Okay, so take 5-6 minutes to work on these, and then we'll take them up in a little bit. So please stop the video now. Okay, we're back. So let's see what we're going to do here. And first of all, we're looking for x-intercepts. Okay, and let's remember what's special about you if you live on the x-axis. Your y value is 0. So step number 1 is to just replace y by 0. So question is can I solve for x? And because it's in this form here, you actually can, because the x is already isolated in some ways. There's no x squared directly on it. There's no other x value. Okay, so what we can do is when I say use good old-fashioned algebra, what I mean is that you can use opposite operations. Okay, so in other words, reverse bedmass. So first thing we're going to do, take care of addition subtractions. So I'll bring that negative 8 to the other side, make it positive 8. Okay, next thing is multiplications and divisions. So let's take this 2 and divide it to both sides. Next are the exponents. Remember, I'm doing reverse bedmass, so we got to take care of this square. What's the opposite of squaring? Well, that's just square root. But this is where we have to be careful. Remember what we saw earlier on is that when I take the square root of both sides, there's nothing here that says things have to be positive. So when I take the square root, I actually have to take the positive or negative square root of 4. There's 2 possible answers. So x minus 3 could be equal to positive 2 or negative 2. And so that means when I complete my final step, which is to take care of that thing that was in the brackets, x can be equal to 2 plus 3, or x can be equal to negative 2 plus 3. Okay? And we shouldn't be surprised that a quadratic function could have 2 x-intercepts. We know that that's definitely possible. So x is equal to 5 or x is equal to 1, because negative 2 plus 3 is 1. All right. Now, when you did the second one, I hope you saw that something a little funny happened. Because if I do the same thing, again, replace y by 0, so 4x plus 2 squared plus 1, and if I just kind of go about my business and do what I did before, bring over the 1, so it's negative 1, okay, x plus 2 squared, whoops, there's no negative there, okay, then divide both sides by 4, and this is where we're going to run into the problem, because if we try to take the square root of both sides, we end up trying to take the square root of a negative number. So we have no solution here. And what I asked you to do in C is to explain why this makes sense geometrically. Well, we can explain that because we can look at this as being a transformation of y equals x squared. And what happens when I take y equals x squared and I transform it? Well, this 4 is going to make it thinner, okay? Because we're multiplying by something bigger than 1. And what do the 2 and 1 do? Well, x plus 2 is going to move it to the left by 2 units, and the plus 1 is going to move it up by 1 unit. So my new parabola is always going to be above the x-axis, okay? So here we see, remember, lines had to have, linear functions had to have an x-intercept, whereas parabolas sometimes may not. If the minimum value is above the x-axis and it's opening upwards like this because it's a minimum value, there will be no x-intercepts. And what's nice is that the algebra will tell you that if it's done correctly. Okay, so that's it for this one. If there's time left over, you can start working on the homework.